All right, we're going to talk about solids of revolution. They're solids formed by revolving a region in a coordinate plane about an axis. So, for instance, if you take that little rectangle that you see on the screen and you revolve that about the line that it's sitting on, maybe that line's the x-axis, maybe it's some other horizontal line. But when you do that, you get what's called a disk. But it's not, it's really a cylinder. It's a really short cylinder that's not sitting on its base, right? The bases are the circles. It's not sitting on one of the bases. So it's actually kind of sitting on, well, sort of its height, but it's a cylinder. We'll call them disks, but they're cylinders, okay? Let me stop this here. All right, now, for the cylinder, do you remember what the area of the volume of a cylinder is? It's pi r squared h, okay? Now, I'm not sure I can still write with this. I had to do a system restore on my computer. I'm not sure it works. But the radius of the cylinder would start here and end here, wouldn't it? Okay? So whatever that y-coordinate is, that's the radius, isn't it? Whatever that y-coordinate right there is the radius. Okay? What would be the height of the cylinder? This right here. The dx is actually the height of the cylinder. So if you're using pi r squared h, so that'll be the r squared, that'll be the h, and that's what it'll look like. Okay? All right, so now there's that same rectangle, but the blue region, the whole blue region, is going to get revolved. That's a solid of revolution. Okay? And its volume is, guess what? In there. Find the volume of a single disk, like that. We can find the volume of that one. We figured it out a while ago. Can we find the volume of all of those? Yep. Can we add them together? Yep. So you see where this thing's going? We're going to accumulate the volumes of the disks. How many disks be? Well, find the limit of that sum as the number of disks goes to infinity. So there's, for all intents and purposes, an infinite number of disks. So think of the integral as an accumulation function again. This time, though, we're not accumulating areas of rectangles. We're going to be accumulating volumes of cylinders, volumes of disks. All right, these things can look different ways. What do you think that one's going to look like? It'll look like one of those chocolate eggs you always get before Easter, right? Okay. Now, I got a question for you. What if instead of revolving it around the x-axis, you revolved it around the y-axis? Would you get the same figure? Not even close. And one more. Can you visualize what that one's going to look like going around the x-axis? Or actually, the x-axis is down here, going around this horizontal line. No, going around the horizontal line. That one that it's sitting on. All right. Now, you were right. If it had gone around the x-axis, you'd get more of a donut shape, wouldn't you? Okay. So, does the axis that it's revolved around matter? It matters a lot. Okay? Because it's going to give you a different looking solid, and if you have a different looking solid, you'll have to reconfigure how you're going to find the radius and the height of each of those cylinders. Okay? But do notice, let's go back to the original one, I think it was this one. Do notice that the radius is going to be the distance from the axis to the far edge of the rectangle. That's the radius, isn't it? The height is going to be the width of the rectangle. If the rectangle was horizontal instead of vertical, let's just say that our axis was there, the radius is still going to be the distance from here to here, and the height is going to be the width of that rectangle. Yeah, when we get ones that look like a donut, we call those figures, we call those washers instead of discs. And you have to subtract out the volume of what's not there. Okay? We'll get to that. All right, you guys with me? All right, so turn to page 456. So like we just talked about, if you have a rectangle and it's sitting on the axis of revolution, when you revolve it, you get a disk. The disk is really a cylinder. It's a really short cylinder, and it's not sitting on one of its circular bases like you tend to think of cylinders doing. It's laying on its side. So to find its volume, we'll need to know the radius of the cylinder, and we'll need to know the height of the cylinder. We'll need to know the radius, the distance from the axis of revolution to the far edge of the rectangle, and we'll need to know the height, the width of the rectangle. All right, I wrote lots of notes. All right. When a region in a plane is revolved about a line, the resulting solid is called a solid of revolution, and the line is called the axis of revolution. If a rectangle is revolved about an axis that is adjacent to one end of the rectangle, a right circular cylinder or disk is formed. It's a cylinder on its side. The volume of this disk is volume equals pi r squared h. Pi times whatever the radius is, and the radius will be a distance squared, and then the h, the way I've got that rectangle, would be delta x, or what do we usually write instead of delta x? Dx. Now, when a region is formed by y equals f of x, so this, x equals a here, and x equals b here, and then is revolved about an axis of revolution, or axis of revolution, got it, a solid of revolution is formed. All right, so take that whole region and revolve it around, you get that solid like we just saw. Okay? Yesterday and the day before, we were practicing drawing in rectangles when we were finding the area between two curves. And you probably thought, well, I can figure this out. I don't really need to draw in the rectangle. You really need to draw in the rectangles now, because you've got to see how the rectangle's positioned for a couple reasons. You've got to know what the distance from the axis to the far edge of the rectangle is, because that's the radius, and you got to figure out the height of the cylinder. Is it a dx or is it a dy? Because that's different. Okay? So always draw in a rectangle. Always, always, always. Now, it gets mathy here, but the volume of this solid can be approximated by placing discs in the solid to approximate the shape of the solid, and then adding all the disc volumes together. So, that's the volume of one disc, right? Pi r squared h. So pi r squared dx. Then find the sum of all that, and that's the sum of the volumes of those cylinders. But that's for a finite number of cylinders, okay? And by the way, look here what I'm doing. Pi is a constant. Are we allowed to factor constants out? Sure enough, put it in front. So you've got pi times the sum from I equals 1 to n of the radius. As long as our axis of revolution is horizontal, the radius will be a function of x. It'll be f of x. Isn't that what would happen up here? Isn't that distance right there whatever that y-coordinate is? And isn't that y-coordinate found because it's a function of x? So if you've got a horizontal axis of revolution, your radius will be a function of x. Okay? Squared, and then times the height of the disk, the height of the cylinder. Now, like I said, that's for a finite number of disks. That's not good enough. That's just an approximation. So take the limit of that sum as the number of disks approaches infinity. And look, all of this is the definition of a definite integral, isn't it? Well, the pi doesn't have to be in there. But the limit as n approaches infinity of the sum from I equals 1 to n of something dx, that's the definition of a definite integral. So all of that becomes the integral from a to b of pi, but put the pi in front because it's a constant, times the radius squared dx. All of that's for a horizontal axis of revolution. Well, look what changes. If you've got a vertical axis of revolution, then your rectangle would go this way, so the radius, the distance from here to here, would be an x-coordinate, not a y-coordinate. And so we would need to have our functions written as functions of y, so we could call it f of y. And then the width of that rectangle, which is the height of the cylinder, would be a dy. So if you have a vertical axis of revolution, everything just switches to y's. You need to put these two things for sure in your notes. Along with memorizing what I just told you to write down, if you always draw in your rectangle and just figure it out, you'll get it in terms of the correct variable, okay? So you're going to have to draw the graphs. You're going to have to draw in a rectangle. Make sure that your rectangle is perpendicular to the axis of revolution, and then you can figure out, and then start with the dx or the dy. Once you know that it's a dx or a dy, you know which variable you need to have in your problem. We'll maybe not even have to deal with that. Okay. I mean, we can have an axis of revolution that goes through a region. I'm not thinking it's going to happen. We'll have to see. Okay? All right. Because you don't really, if the two sides aren't symmetrical, you won't really get a solid out of that when you rotate it. You know what I'm saying? Well, but then, see what would I don't know what would happen if we had that region revolved around that axis. I don't know, as this one is going around magically becoming solid as it goes, then what's this one doing? I don't know. Okay? Well, why are y'all assuming that's what would happen? You know what I'm saying? Why are you assuming that the big one would be the solid part and just ignore that? Why would you ignore that? What I'm saying is, I don't think that would be something we call a solid of revolution. Okay? Y'all follow me? All right. I think we've talked about all that. Talked about that. Showed you that one. Let's do number 4. On page 463, it says set up and evaluate the integral that gives the volume of the solid formed by revolving the region about the x-axis. So, draw the graph. If they don't give you the graph, you graph it on your calculator and then draw it on your paper. Okay? So y equals the square root of 9 minus x squared. And the directions say that we are revolving this about the x-axis. Get in the habit of writing down what your axis is, because it's going to move around after a few problems. Okay? It's not always going to be the x-axis. It's not always going to be the y-axis. It might be the line y equals -2. It might be the line x equals 4. Okay? So, draw your graph, write down your function, write down what the axis of revolution is. You need all of that. The graph, the function, the axis of revolution. Because like we talked about when we were showing those little animations, if the axis of revolution is different, you get a different figure. So that's a fairly big deal. All right, the first thing I decide once I've got it drawn, draw in a rectangle that's perpendicular to your axis of revolution. And figure out whether the width of that rectangle is a dx or a dy. It'll be one or the other. There's no other choices. So this one's a dx. That means the height of the disk that's going to be formed when this thing gets revolved is going to be dx. The height is dx. That also tells us then that our variable when we work out our integral has to be x. It can't be a y with a dx, can it? Remember that whole separation of variables thing we did? We can't work an integral with a y and a dx. So it's got to be x's and dx. Okay? Now, we know what the height of the cylinder is. It's dx. We know that it's pi r squared h for the volume. Pi, not a problem. H is dx. R. We need r. So, the radius is the distance from the axis of revolution to the far edge of the rectangle, or the outer edge of the cylinder. So that little red segment right there, its length is the radius. But here's the thing. If I drew in a different rectangle over here, I would get a different length for the radius, wouldn't I? So I'm not looking for a constant. I'm looking for a function. Okay? In each case, isn't that length whatever that particular y coordinate is? So, if we were allowed to just put y into our problem, we would. But that's not a good idea because I can't integrate y dx. So instead of putting y, I put what y equals. Okay? So it seemed like that was going to be a problem there for a minute, didn't it? Is it? It's not. So our volume equals pi times the integral. Now, I do need limits of integration. This doesn't go on forever. So what are the boundaries of our region? Well, x equals 0 is one boundary. X equals 3 is the other boundary. So the integral from 0 to 3 of the radius squared, the radius is y. But I can't put the letter y, so I put what y equals. So the square root of 9 minus x squared, that's the radius squared, times the height of the cylinder. And the height of the cylinder is always dx or dy. In this case, dx. So that's pi r squared h. Make sense? All right, well, we can do that. In fact, that's an easy one. When you square the square root, you get the radicand, 9 minus x squared. All right, just don't forget that pi out in front. So volume equals pi times 9x minus 1/3 x cubed, evaluated from 0 to 3. So volume equals pi times, well, evaluate for 3. So 9 times 3 is 27. 3 cubed is 27, but negative 1/3 times 27 is a negative 9. So 27 minus 9, minus 9 is what I get when I evaluate for 3. Minus sign, evaluate for 0. Well, 9 times 0 is 0. 0 cubed is 0. Negative 1/3 times 0 is 0. 0 minus 0 is 0. Well, 27 minus 9 is 18. So pi times 18, 18 pi. Now, they don't give us any units, but if we had units, what would we do with them in our answer since it's volume? Units cubed. All right, now, that's as easy as it gets. We okay on this one? Okay. Any questions? All right, number 10. This time, we're revolving around the y-axis. Are things going to change? Yes. So set up and evaluate the integral that gives the volume of the solid formed by revolving the region about the y-axis. They made this about as easy as they could make it, because they gave us this as a function of y instead of a function of x, and we don't have to convert it. Okay? All right, so draw the graph, draw in a rectangle that's perpendicular to the axis, and tell what axis you're using, and tell what your function is. So graph, rectangle, axis, function, in whatever order you put them down. Okay? So we're going about the y-axis. X equals negative y squared plus 4y is our function. We've got our graph. They gave it to us. Thank you, book. That was nice. Draw in a rectangle that's perpendicular to the axis of revolution. So that's perpendicular to the y-axis. All right? Now, once you've got your rectangle, is everybody caught up with me? You got your graph, you got your rectangle. You got to decide what the width of that rectangle is, because that's the height of your disk, and everything depends on using the correct variable. The width of this rectangle is dy, which means the height of this cylinder is dy, which means we have our integral with a dy at the end. If our integral has a dy at the end, everything else in the integral has to be in terms of y, not x, doesn't it? All right, so everything's y's. Okay? All right, now, what is the radius? Because the h kind of takes care of itself, right? When you decide what the width of the rectangle is, you figured out h. Pi is pi. R is what it's all about. Okay, that's what you got to figure out. So we've got the h, we've got the pi. What's r? The radius is the distance from the axis to the far edge of the rectangle. And you only need to draw one rectangle in. But look, if I did draw another one, it would have a different radius. I'm telling you that so that you'll realize you're not looking for a constant. You're looking for a function. Okay? Almost always the radius is a function. I mean, it could be a constant. If that was a vertical line, it would be a constant if that was the edge of our region. But, that's just not going to happen very often. So you're looking for a function. Now, the distance from here to here is whatever that x-coordinate is. The distance from here to here is whatever that x-coordinate is. But I can't use x because I've got dy in my integral. So instead of using x, I use what x equals. Negative y squared plus 4y. So, volume equals pi, just always put it in front, might as well, times the integral. Now, our limits of integration don't need to be x coordinates, do they? They need to be y coordinates. So what's the lower limit of integration? It is. It's 1. What's the upper? 4. So the integral from 1 to 4 of, now, radius squared. I would have liked to have written x, but I can't because I've got a dy for our height. Okay? So instead of x, I put what x equals. So negative y squared plus 4y. But remember now, it's not just radius, it's radius squared. Is that it? Is that our integral? That's our integral. Well, we're not done with the problem, but that's our integral. All right, any questions? Okay. You got to do some thinking, don't you? Okay, you really do. Don't be afraid to think. Okay? Thinking is more important. I mean, having what I told you to put in your notes memorized is important. But being willing to think every time you draw a graph and work it all from bottom up every time, that's the key. All right? So we square that. So volume equals pi times the integral from 1 to 4 of y to the 4th minus 8y cubed plus 16y squared. That's what we get when we square it and simplify. Trust me. And now we integrate. So volume equals pi times, well, what's the antiderivative of y to the 4th? 1/5 y to the 5th. What's the antiderivative of negative 8y cubed? Negative 2y to the 4th. And the antiderivative of 16y squared? 16/3 y to the 3rd. Don't forget, evaluate it from 1 to 4. All right, and you may find a calculator helpful at this point. We evaluate for 4 first. So volume equals pi times, all right, 4 to the 5th is 1,024. So that's 1,024 fifths. And then 4 to the 4th times 2 is negative 512. And 4 to the 3rd times 16, hey, wouldn't that have to be the same thing as 4 to the 5th? 4 to the 3rd times 16? So 1,024 again. This time it's over 3. That's what we get when we evaluate for 4. And if you want to use your fraction abilities on your calculator to evaluate all that in one step, I got no problem with that. The only trouble is if you mess it up, you'll never know where you messed it up. But, you know, minus, then evaluate for 1. So that'll be 1/5 minus 2 plus 16/3. And then I did use the fraction capabilities on my calculator to find that in the first parentheses, that all simplifies to be 512/15. And the second parenthesis simplifies to be 53/15. Now, don't forget about pi still being in front, and don't forget that this is a volume. So 512 minus 53 is 459. So I can write the volume as 459 pi over 15. But if 459 over 15 simplifies, I want to simplify it. I'm not the AP test. I want to simplify it. And what is 459 over 15? 153 over 5. All right. If this were a free response question on the AP test, you could have stopped right there. And as long as you don't have to use your answer in any way, fine for the AP people. All right. We cool with 10? All right. Let's do number 11, part C. Number 11, part C. Says find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the given lines. So we have y equals the square root of x as one boundary, y equals 0, that's the x-axis, as another, and x equals 4, a vertical line. And then the axis of revolution is not the x-axis or the y-axis, it's the line x equals 4. So draw the graph. It'll look something like that with the line x equals 4. You draw in a rectangle that is perpendicular to the axis of revolution. That's the axis. So your graph ought to look something like that. You need the graph. And you see, too, that I wrote here that I wrote disk. That's because when you do the rest of number 11, you'll be using the washer method for a couple of these parts. So once we learn the washer method, we'll need to start labeling which method we're using. It helps keep you straight, okay? But that's the reason I wrote that. All right, so I've got the graph. I've got the line. I've written that it's about the line x equals 4. I've got my function, y equals the square root of x, written on here. Now, the width of that rectangle, the height of that disk, dx or dy? dy. So, my function is written as a function of x, isn't it? Y equals square root of x. I need to change that. Square both sides, and you get x equals y squared. Now I've got it written as a function of y. Okay? Now, pi is pi, h is dy. We'll figure out our limits of integration in a minute. R. R is where it's at. R is the distance from the axis to the far edge of the rectangle. That's R. Now, it's not simply that x coordinate, is it? That's not what it is. We're going backwards, okay? Instead of measuring from starting from a 0 on the left and moving to the right and measuring, we're going the other way around. So let's do a little thinking. So in other words, we're going to have to subtract, okay, because we're going the wrong way, okay? Now, if, big capital I, if our rectangle went from here all the way over here to the y-axis, what would that length be? It'd be 4, wouldn't it? So if I start with the concept that it could be 4, and then I subtract out the missing distance, wouldn't that tell me the radius? So 4 minus what? 4 minus x, but that's the function. 4 minus the function gives me the radius, doesn't it? Okay? Look, if I could, I would call the radius 4 minus x. I would. But can I integrate that considering I've got a dy? Nope. So instead of 4 minus x, I put 4 minus what x equals, y squared. Okay? So r is 4 minus y squared. Now this is big, and this is fairly complicated. Let's face it, it is. Y'all following me on why that's the radius? Now let's write the integral. Okay? So, volume equals pi, integral sign, dy at the end. I know all that for sure, don't I? I also know that it's the integral of the radius squared. It's pi r squared h. So I've got the pi, I've got the h, it's r squared. So that's got to be 4 minus y squared squared. But I still need my limits of integration. Should my limits of integration be x coordinates or y coordinates? Y coordinates, because everything's in terms of y. So what's the lower limit of integration? What's the lower boundary in the y coordinates? 0. Upper? Question? It's because up until now, it was on either the x-axis or the y-axis. Okay? But now, since the axis of revolution is not either the x-axis or the y-axis, we've kind of got to recalibrate how we find the radius. That's the reason I've been saying to you, it's the distance from the axis to the far edge. If you can think of it as that, instead of thinking, oh, it's always the function, then you got a shot. Now, is the function always going to be involved? Yeah, it is. But it might be, in this case, it's 4 minus the function. Yes. I can't think of an exception. I'm not saying there's not one, but I can't think of one.
How do we know?
Because x equals 4 is a boundary. If x equals 4, y equals 2. That's our boundaries, right? That, and that. So that function equals that function when y equals 2. Okay?
So constant the line of x equals 50, the radius is
Exactly. If that was a 6, the radius would be 6 minus y squared. Y'all catch that? If the axis was x equals 6, that'd be 6 minus y squared. Make sense? If we change the 4 to a 6, we're not ready for a gap. We're not ready for a gap yet. Those are washers. Okay? So if all the 4s were 6s, we would have put a 6 there. All right. There's the rest of it. And there's your assignment.